So we will have final review on Thursday. This is just a couple simple problem sets to do with the reactions in chapters 11 and 17. Some nice practice for the final also. So we're just in that mode. I will take and readjust all the points and stuff like that appropriately. So it'll all work out. But, gee, sorry. All right. This states very clearly that we're dealing with SN2 reactions. Remember, when you're dealing with a substitution reaction, you need to identify a nucleophile. In this case, the first reaction here, that's going to be phenoxide. That's going to attack the electrophile. And here, this is the benzyl carbon. That's the electrophilic center. And the bromine is termed the leaving group. Remember that in a simple SN2 reaction, all we have is the nucleophile attacking the electrophilic carbon, and the bond to the leaving group breaks. It's a concerted reaction. The bond making and bond breaking all happens in the same transition state, and that's why it's bimolecular. Very simple, attack, leaving group leaves. This is the product, it's an ether. The bond that we made in this is this guy right here. This is generally termed the Williamson ether synthesis. Very, very simple reaction. I have no idea how Williamson managed to get his name attached to it, but it's a very simple SN2 reaction. Our next one is also a simple SN2. Our nucleophile here is going to be the Phenoxide Anion. We're attacking the primary carbon. Remember, SN2 reactions work best at primary centers. They go slightly at secondary centers, and they really don't work at all at tertiary centers. So the phenoxide attacks the carbon, bromine leaves, and again we make the simple ether. This is the bond we made, just in case you're keeping track. Our last one here, we're going to make a carboxylate ester. The carboxylate anion is our nucleophile. This is a triple bond, the CH2 next to it. If this was a double bond out here, we would call this an allylic center, wouldn't we? Well, this is the triple bond version of an allylic center. You will learn when you do conjugated systems that allylic centers such as this, same thing with benzoic, are very reactive towards SN2 reactions because the orbitals just line up very nicely. Again, the oxygen of the carboxylate will attack the carbon, and we simply make the ester. Again, this is the bond we made. It's always nice to be able to keep track of that. Any questions? Oops. Any questions on that set? All right, here we have more simple SN2 reactions. Our first one, we're using ammonia, the nitrogen and ammonia, as our nucleophile here. The basic reaction is going to be the lone pair on the nitrogen attacking the electrophilic carbon. The bromine is going to leave. If we had a single mole of each, we would expect to get the single substitution product. The fact that you put the word excess here tells you something. It tells you that you want to do this reaction over and over and over again until basically you fill up your nitrogen. Here I've stopped at the tertiary amine. Remember, you could also do one more and make the quaternary ammonium salt. On an exam, either one that you put would certainly work. Remember, this still has a lone pair of electrons and can react with another bromoethane to give another mole product. Any questions? This next guy here is designed to test your knowledge on the stereochemistry of the SN2 reaction. Iodide is our nucleophile. This is going to be our electrophilic carbon. Remember, it's a secondary center, so it's not a great reaction, but we can get it to go. The thing you have to remember is that the SN2 reaction proceeds with inversion of configuration. So what you have to do is simply draw this somehow so that you can demonstrate that we do have inversion. Oh, I forgot to say this. Substitution occurs 3 times to get this. First, we get the single ethyl group attached, then we get 2, and then the final product. Any questions? All right, let's go back to this one. All I've done is take the bromine, which was pointed back, put it forward, again on the same side now, cis to the methyl group. That's a stereochemical inversion. On the final exam, you should be able to look at these guys and be able to assign RS configurations if you were asked. But remember the thiols. Sulfur is right below oxygen on the periodic table. Makes it much more polarizable. It's a darn good nucleophile. All we're going to do here is a simple SN2 reaction. The hydrogen sulfide anion will displace the chlorine, and we'll wind up with the thiol as the product. Any question on this set? All right. Once again, we have a nitrogen nucleophile. We have a secondary center. This isn't going to be a great SN2 reaction, is it? Because we have lots of steric hindrance in here. I've also just indicated single mole quantities. Again, that's a hint to you. If you're dealing with a single mole of each, what you just want to do is do the reaction one time. Remember, we will have a lone pair of electrons in our product. We could do it a second time, but this kind of tells you just do it once. Again, the nitrogen is going to attack. We're going to lose a proton off the nitrogen in the second step, and all we're going to do is make the substituted amine. Our nucleophile here is an alkynyl lithium. Oops, we're supposed to see the product yet. Remember, the hydrogen on an alkyne, a terminal alkyne, is acidic. Now it has a pK of about 20, so it's not really real acidic, but we can pull it off. Here we've simply replaced it with a lithium. You should regard this as a simple carbanion. The only really tough part about drawing the products in a reaction like this is remembering that we're going to have a bond directly from our alkyne to the electrophilic center. Here's our alkyne, here's the bond that we just made to the electrophilic carbon. Sometimes people get mixed up and put in an extra carbon. Any questions? All right, SN2 reactions we said were nice civilized ways to do substitution. A nice civilized way to do elimination is an E2 reaction. Things we want to remember about an E2 elimination. The leaving group and the hydrogen that's pulled off must be coplanar, and they must be anti or trans to each other. Those are the things you need to remember. I will pretty much clearly label, as I've done here, when I want something like E2 and stuff like that, as opposed to SN2. You can also pretty much guess just by looking at the reaction conditions. This is terbutoxide and terbutanol. Remember, this is the magic solvent mixture for E2 elimination. The terbutoxide is a very nice strong base, but it is a lousy nucleophile just because it's so big. So what's going to happen here, we're going to pull a hydrogen off on the carbon that's adjacent to the leaving group. This is how you know what to do. This is our leaving group here, the bromine. We're going to pull a hydrogen off the adjacent carbon, right here. And when it does, we're simply going to eliminate the elements of HBr, and we will make an alkene. Recall that TS stands for tosylate, that's toluene sulfonate, commonly used as a leaving group in both SN2 and E2 reactions, also unimolecular reactions. It's a very nice leaving group, very good leaving group. Again, TS is just the abbreviation. There are two possible ways we can do this elimination. If this is our leaving group, we could say we're going to pull the hydrogen off adjacent to that. That could be here on the methyl group, or it could be one of these ring hydrogens. Remember, Cyclohexanol's rule says that we will always want the most highly substituted alkene. If we pulled off a hydrogen on the methyl group, and now the advantage for that, frankly, is that this is much easier to get to than these guys are. But if we pull this guy off, we would have the exocyclic alkene, and that would not be the most highly substituted. Any questions? Cyclohexanol's rule. Oops. This isn't supposed to happen. Well, let's look at this one because I think it is going to happen. Let's look at this reaction. If we simply looked at this and said, okay, bromine is our leaving group. We're going to pull a hydrogen off an adjacent carbon, and we just, in fact, we still have Cyclohexanol's rule sitting here on the board. So we would expect the most highly substituted alkene to be here at the tertiary center across this way. Actually, however, instead of forming the most highly substituted, this is like an anti-Cyclohexanol product because we're forming a conjugated system. Now, we don't quite know what a conjugated system is yet. I believe that's covered in chapter 12, which we do next semester. But conjugated system basically means we have double bonds or sp squared carbons adjacent to each other. This allows overlap of the adjacent pi systems, and that's a very stable situation. So this gives us the anti-Cyclohexanol product simply because we're making the fully conjugated system. Any questions? Here we have our leaving group, that's our bromine. We need to choose which hydrogen we're going to pull off here. Here we have hydrogen on an ethyl group adjacent to the ring. Here we have hydrogens that are in the ring. The product of this reaction is actually this guy. This gives us a tri-substituted alkene. If we had pulled off one of the ring hydrogens, we would also have a tri-substituted alkene. So this follows Isef's rule, it's fine, but both products do. This one is favored over this one simply because, well, for two reasons. This hydrogen is much easier to get to because it's dangling out from the ring. This guy also, remember, we're going to have to make the leaving group and the hydrogen coplanar. This is a 6-membered ring. So we're going to have to pucker this thing so it's axial if we want to pull off one of these hydrogens here. So that takes more energy. So this guy is much easier to get to, much easier to do the elimination, and this is the major product. This is a dead simple Zaitsev problem. Again, we have a secondary center here, tertiary center here. Secondary center is easier to get to. This gives us the more highly substituted alkene. As Zaitsev says, that's what we should do. Now with this guy, we have a methyl group, and we have a bromine here. Bromine's our leaving group, right? We could imagine pulling off this hydrogen. That would give us a double bond across here, right? That double bond would be tri-substituted, and that's good. However, this is an E2 elimination, isn't it? And because it's E2, the bromine and the hydrogen have to be trans to each other. What's trans on this side? Well, the methyl group is. The hydrogen that we'd have to pull off is cis. Oops. I just gave a beautiful argument for the wrong product. Well, I drew the wrong product. Actually, this is going to give elimination across here. To give not this alkene, but this one up here. So the double bond will be not with the methyl group, it'll be up there. Sorry, I drew the wrong product. But the reason is, this hydrogen, again, is cis to this bromine. That doesn't work. They have to be trans. Only trans hydrogen you can get is up here at this point. So change your double bond here up to this position. Two more simple eliminations. Once again, we have a bromine here. This bromine, what is trans to this bromine? Well, the methyl group up here, so the hydrogen is cis. Just like the argument that I made properly on the previous problem, that means that we have to pull off one of these hydrogens in order to make, oh, come on, come on. Why does PowerPoint do this sometimes? This hydrogen is trans. Methyl group is trans up here. Therefore, this, just like on the previous problem, is what you're going to form. For the second one here, this methyl group is cis to the bromine, which means that the hydrogen here must be trans. So this can go and give us an elimination to give us the side step product that looks like that. All right, any questions? Your final exam will also have simple synthesis problems. So let's go ahead and look at some simple synthesis. What I want you to do here is to give me two possible starting materials, two possible alkyl bromides that we could do an E2 elimination on and make styrene. So on the exam, this would have 2 boxes, 1 for each. All right, well, the logic here, we know we're going to do an elimination. It's going to be an alkyl bromide. In order to form the alkene, the bromine had to be on one of these alkene carbons. We have 2 alkene carbons, so it's not too difficult to come up with 2 possible leaving groups. If we had this as our starting material, so putting the bromine here, we could pull off this hydrogen, do a trans elimination. We could also simply have this as our product, where we put the leaving group here at the terminal position, pull off one of the benzylic hydrogens, the bromine leaves, to give us the same product. So the logic here, when you look at an elimination reaction, you're making an alkene. As long as it's E2, you know that the halogen was attached to one or the other of the alkene carbons. Any questions on the logic? Here's another synthesis problem. Here we are doing a Williamson ether synthesis. So we're making a simple ether. And I ask you to give me 2 possible alkoxides. And we're going to make this product. Again, it's an SN2 reaction. What you need to do is remember that we're going to use an alkoxide and an alkyl halide. When we made this ether, we made one of these bonds on either side of the oxygen. So just take one of them and split it. If we split here, then our alkoxide was this half of the molecule, and the alkyl halide was on this half of the molecule. So this pair, methoxide and bromocyclopentane, would give us this product. Now the other side, if we split here, that means the alkoxide was this half of the molecule, and the alkyl halide was simply attached to the methyl group. So the other possible pair would look like this. And again, this is the bond that we made. So the 2 alkoxide alkyl halide pairs would look like this. Any questions? Let's do it again. For an elimination reaction. Go ahead and give me an alkyl bromide, then we can do the elimination and make this as our product. Logic, once again, is simple. Halogen was attached to one of the alkene carbons. All you have to do is get rid of your double bond and make your two possible alkyl bromides. Our first one would look like this. We pull off hydrogen, do the elimination. Second one would look like this. Once again, pull off the hydrogen and do the elimination. With our top one, we could possibly expect to get elimination across here as well. But like we saw earlier, this hydrogen is so much easier to get to. And we'd have to stick this guy axial in order to do a ring elimination. So the exocyclic is probably preferred. Any questions? All right, I'll hush for a second. Go ahead and take this ether apart and give me the two pairs of products. The exercise simply is to find your oxygen, and remember we're going to split on either side. Let's split here. That means that the alkoxide half is basically this, and the alkyl halide half is simply this 2-carbon unit with a halogen. Two-carbon unit, so bromoethane. This is isocarboxide, simple SN2 reaction. If we now split at the other side, then the alkoxide was this half, so this is ethoxide. Here we have a isopropyl unit with our leaving group attached, and that should work. Again, simply split on both sides of the oxygen. Any questions? Go ahead and do another elimination. Give me the two possible products or reactants. All we have to do is simply put our halogen on each of these carbons. Our first one could be something like this. Now, as you do this elimination, remember, this is the site-F product. So the hydrogen we're going to pull off is going to be this guy up here to give us the most highly substituted. The same thing down here. We're going to put the halogen right here on the triple center. Now, we could imagine pulling a hydrogen off one of the methyl groups, but that would not give us the most highly substituted one. Most highly substituted would be pulling off this hydrogen to give us this product. Any questions? All right, now we're making a ring. Even though we're making a ring, the logic is still the same, isn't it? What you're going to do is simply say to yourself, it's a Williamson ether synthesis, and we're just going to split on both sides our oxygen. One side would be the alkoxide, the other side would have the leaving group. So, let's split up here. That means that the leaving group, the halogen, would be attached up on this carbon, and that this was an alcohol or an alkoxide. Okay? So, molecule would look something like this. Alkoxide half, and our leaving group up here. Reaction, oxygen simply attacks, and bromine leaves. Now if we split on the other side, we're splitting down here. This was the alkoxide. And this center here, the secondary center, is where the leaving group was attached. So the reactant would look something like this. This attacks. Well, these two are reversed, aren't they? Oh, well. Any questions? Let's go ahead and make the exocyclic double bond here by an E2 elimination. Now, the logic that we've used over and over is that the leaving group was attached to one carbon or the other. But here it actually does make a difference. We're only going to draw one reactant because the other one doesn't. Your job is to figure out which one works. One that's going to work for you here, we're going to have to, we're not making, well, this is not the most highly substituted double bond that this molecule can make. Therefore, what you're going to have to do, is use this as your starting material with the leaving group out here. Remember, this is an E2 elimination, no rearrangement. That means that we're going to pull off this ring hydrogen. This is going to leave to make the heterocyclic group. If instead we had put the halogen on this carbon, we would be more prone to pull off one of the trans ring hydrogens and make the most highly substituted alkene. All right, let's do one more SN2 reaction here. Give me an alkyl halide that we could use to make this. Our second reactant here is given as methylamine. In chapter 24, you will call this methanamine. Well, we know that we can make substituted amines by an SN2 reaction just with a leaving group, okay? Here we must have a leaving group on two different carbons. This is the chunk that comes from the methylamine, which means that we did this and this as our bond-making events. So that we must have a leaving group on each of these carbons. Split on both sides, leaving group here, leaving group here. That is our second reactant. Again, the nitrogen will displace it this way. And we make our cyclic product. Any questions? Now, since we didn't have the pleasure of having our third exam, on the final, we are also going to have a bit of nomenclature for simple alcohols. This one we haven't done yet, but it's very, very simple. Remember, when we're doing nomenclature, the longest continuous chain containing the hydroxyl group, we use OL to indicate it's an alcohol, and we want to give it the lowest number. If we look at a sample here, our longest chain must contain the alcohol, so it's going to be that. We want to give it the lowest numbers. We want to start numbering out here by the bromine. And we would simply say this was a 1 bromo, 2 hydroxy, and this is a butane side chain. We could call this 1 bromo, 2 methyl, 2 butanol. Remember, you can also move the 2 here down to the functional group at the end and call this a butan 2-ol. Both of these are acceptable to IUPAC. This is actually preferred these days, but both are acceptable. Any questions? Let's just do some quick examples. Take these names and give me a representation. As you look at the name, it's a cyclohexane, isn't it? And it's a diol. So we have 2 hydroxyl groups on our cyclohexane. They're going to be at positions 1 and 3, and they will be cis. You could show that using a chair, or you could simply use wedge bonds. Remember, in Chapter 14, you will learn that a phenyl group is basically a benzene ring. This is a 1-pentanol. So we're going to start off with a parent chain with 5 carbons. And one of the terminals is simply going to have the hydroxyl group. Finally, we go out to carbon number 4, so that's 1, 2, 3, 4, and let's put a phenyl group. You could draw the phenyl group this way as a cyclohexatriene, that's fine, or you could do the shortcut and just put a circle in the middle instead of the double bonds. Again, that's Chapter 14. Our third one here, once again, we look and we see it is a cyclohexanol. So we have a 6-membered ring with a hydroxyl group. In position 4, we have 2 methyl groups. Remember that we want to always give the hydroxyl group the lowest number, so that's why this is carbon 1 and not this guy. Let's do another simple set. Our first one, we look and we see we have a pentanol. Again, it's a 1-pentanol, so 5-carbon chain, hydroxyl group in carbon 1. Simply count out to carbons 3 and 4 and put on methyl groups. We have a cyclopentane parent. It's a diol, so we have 2 hydroxyl groups. They are on carbons 1 and 2, and they are cis. You could draw this with perspective drawings, or you could simply use wedge bonds. Two-phenyl ethanol. Again, our parent here is ethane, so it's a 2-carbon chain with an OH. And in our second carbon, we have a phenyl. So there's our ethanol, carbon 1, carbon 2. Simply draw in your phenyl. Two more simple ones. We're dealing with a pentanol. The hydroxyl group is in carbon 3. Carbon 2, we have a methyl group. And finally, again, this is a pentanol. Hydroxyl groups in carbon 2. Count out to carbon 4 and stick in a methyl. Any questions? Now we're also going to do synthesis of simple alcohols and reactions of alcohols, alkenes, and everything on the final. Fortunately, many of these are the same. Let's just review what we know already. From all all the way back in chapter 7 or 8, I think it's 8. Simple hydration. When we see a hydration, what do we think? We think carbocation intermediate. We think rearrangement. And we think Markovnikov. If your molecule is simple and does not undergo rearrangement, this kind of hydration will work fine. If you have a molecule that is prone to rearrangement, you can avoid that by using mercury 2 acetate. Second step, more hydride, because you wind up with an organic mercurial. More hydride simply gets rid of your mercury. Again, it's Markovnikov regiochemistry, but no rearrangement. Hydroboration oxidation. Again, no rearrangement. The addition is cis for the hydroxyl group and the hydrogen you add, and it is anti-Markovnikov. Permanganate in base, different than permanganate in acid. We did this reaction in lab, wasn't it fun? Remember, we form permanganate as a precipitate, and we get the cis 1,2-diol. We also said we could make alcohols by reduction. There are 2 modes of reduction that we've talked about, borohydride and lithium aluminum hydride. Borohydride is nice and simple. It is not as selective as lithium aluminum hydride is, but typically it works fine. If we have an aldehyde, both of these will give us primary alcohols. Remember, we're just adding H- to the carbonyl carbon. If we have a ketone, we add H-, we have a secondary alcohol. We also talked about Grignards, and we're going to do a bunch of Grignard problems in just a minute. Grignard is R, MgX, where R can be basically any organic group. Second step, you just dump it into water. This acts as a carbanion, adding to the carbonyl. Here we have an aldehyde, and we have made a secondary alcohol. If we have a ketone, do the same reaction, we make the tertiary alcohol. Aldehydes and ketones reduced by borohydride or lithium. Various reagents added to aldehydes and ketones to get primary or secondary and tertiary alcohols. Any questions? We also talked about reactions of alcohols other than the Williamson ether synthesis. Just a couple that we need to remember. If we have an alcohol in the presence of PBr3, what we do is we form an alkyl bromide. This reaction involves the formation of an intermediate phosphate ester. The actual product forming step is an SN2 reaction, bromide attacks, phosphate leaves, and we get our product. Because this is an SN2 reaction, remember it goes with inversion of configuration. This is a classic exam question, so be ready for it. You'll be given a chiral product. Make sure you show inversion of configuration. We can also make an alkyl halide using thionyl chloride and pyridine. pyridine once again. Looks like this, 5 carbons, a nitrogen in the ring. It's a very common organic base and solvent. A bit of a smell to it, but it's very common. This involves the same sort of mechanism. The hydroxyl group will attack the sulfur, and we will form the chlorosulfite ester. In a second step, then, chloride will attack, and we do the SN2 reaction. Once again, inversion of configuration. If instead of doing this reaction in pyridine, we do it in a nonpolar solvent, again, we're going to form the chlorosulfite ester, but because this is a nonpolar solvent, the chloride that's formed does not undergo the SN2 reaction. That simply bubbles off as HCl. Instead, the chlorine here from the chlorosulfite ester simply migrates down in a front side attack called an SNI mechanism, and we wind up with a product, but because it's a front side attack, we have retention of stereochemistry. So thionyl chloride is actually kind of neat because it gives you the power to control your stereochemistry, either retention or inversion. Any questions? We've done a whole lot of examples of elimination reactions. Remember, with conditions like this, we are most likely to do a unimolecular reaction because we're going to form a carbocation. This makes it prone to rearrangement. And again, we would get a Zaitsev alkene here, or if we have substitution, it would be Markovnikov. POCl3 is a much more civilized way to do an elimination. What we're going to do is form a phosphate ester here once again. Pyridine is going to pull off our hydrogen. So here's our intermediate. This is going to be a nice, simple E2 elimination. And because of that, we're going to get, in this case, the nice trans product, the most stable product. All right, finally, let's do oxidations. Remember, our new favorite oxidation tool is called PCC, that's pyrididium chlorochromate. Chromate is actually the oxidizing agent here. But if you do it with the pyridine salt, it makes it a very mild oxidant. That's important because here we can take a primary alcohol and make an aldehyde. Chromate will usually oxidize an aldehyde to the acid, but PCC, because it's so mild, doesn't. Go ahead and let's just run through a set of simple reactions. I think your final exam has like 3 full pages of reactions. So it'll be the standard set of alkene reactions, alcohol reactions, SN2, and eliminations. But we know all those. That's simple, right? All right, we see PBr3. We know we're going to make an alkyl bromide. We say to ourselves, this is going to be an SN2 step. We're going to have inversion of configuration, but we don't have a chiral center, so no big deal. All we're going to do is make the bromocyclohexane. Thionyl chloride pyridine. This is the SN2 version once again. Here we have shown stereochemistry, haven't we? We know that thionyl chloride and pyridine is going to give us inversion. So let's go ahead and show that by just taking our methyl group and sticking it back instead of forward. PBr3, once again, we're going to form our phosphate ester out here, phosphide ester actually out here, do a substitution at this point. Not going to be easy because it's a ring carbon. And we would wind up with this as our alkyl bromide. This is just another way that you could show that. Again, here's our hydrogen coming forward. We started off with the hydrogen coming back. So any way you want to show the stereochemistry works. POCl3. We think for a second and say, okay, this is going to be a nice civilized T2 elimination. No rearrangements, nothing like that. We're going to lose the hydroxyl group. We're going to form a double bond. It's going to come from the adjacent carbon, and it's going to look like that. PBr3, we're making an alkyl bromide again. We have shown stereochemistry, therefore we have to show the fact that we have inversion. Going to replace our hydroxyl group, and again we just have to show inversion. That should do it. This next one is kind of a bad reaction. We see we have a benzyl alcohol here, and we have HCl and ether. The fact that we're ether, we're probably going to, well, there are two possible products here. Clearly, we're going to make the benzyl carbocation armor. Whenever we have a unimolecular reaction like that, we can get two products. We could get substitution from the chloride attacking, or we could get elimination. So an SN1 or an E1. It's almost impossible to push it one way or the other. Really, either product that you show would work fine. This is the elimination. Actually, I might have even done something like show both products from E1 and SN1. All right, here we have pyrididium chlorochromate versus chromate. Chromate, remember, Jones reagent is a very powerful oxidant. We tame it down by putting it as the pyrididium salt. The real distinction is that PCC will oxidize and stop at the aldehyde stage, and chromate will not. So for our top one, we're simply going to convert this carbon into a carbonyl, and it's going to stop at the aldehyde stage. For this guy, we are going to make an intermediate aldehyde. Yes, we are. But the aldehyde will be very, very rapidly oxidized by the chromate. So this is going to be a carbonyl, but instead of being an aldehyde, it will be a carboxylic acid. Any questions? All right, remember all the fun we had making ethers with the Williamson ether synthesis. Let's do the same sort of thing here with a Grignard reaction. In this type of problem, I give you an assortment of starting materials, and I simply want you to identify 2 potential carbonyl starting materials and 2 alkyl halides or whatever, 2 Grignard reagents that you could use to make this compound. So, the logic here is, this is the OH group. This is the alcohol that we formed. That means that this used to be a carbonyl, and that we made a bond to that carbonyl from one side or the other. We're looking at an aldehyde, because it's secondary alcohol, can react with our Grignard to form the secondary center. So in our collection up here, we want to only look at the aldehydes. Start off by splitting on one side. This half was our Grignard reagent, and this half was our carbonyl. So we look up top. Here we had a carbonyl. It was an aldehyde, benzene ring. It's benzaldehyde. Our Grignard reagent is simply this chunk with a magnesium bromide attached. Now we'll go ahead and split on the other side and come up with the other pair of reactants. Once again, we're going to be looking for an aldehyde. The aldehyde, this was a carbonyl, hydrogen attached, and we have this isopropyl. The one that works up here is this guy, and that means that this half was our Grignard reagent, so that's simply phenyl magnesium bromide. Go ahead and do the same exercise with this guy. We have a secondary alcohol, so we're looking at aldehydes. Again, split on one side or the other. This was the aldehyde portion, so we have a carbonyl and a benzene ring. And once again, we have benzaldehyde. Our Grignard reagent is the other half here, so it's a 1, 2, 3 carbon chunk with a methyl group attached. Simply substitute magnesium bromide at this point, and that's your reaction. Split on the other side. This part used to be the aldehyde, so we're looking for aldehyde, CH2, and then an isopropyl sort of thing. The one that works is right up there. And this was our Grignard reagent, Fiddle magnesium bromide. For aldehydes, get a split on one side, and we split off the isopropyl group, so we have 1, 2, 3 carbons in a row, and it's an aldehyde, so it's that guy. Isopropyl half was our Grignard. Split on the other side. Identify your products. Here we have a carbonyl, and this is the isopropyl, hydrogen dangling off there. I think that works up there. Our Grignard chunk was simply the 2 carbons, so an ethyl, magnesium bromide. Secondary alcohol, so we're looking for aldehydes. Split on one side. For some reason, people tend to miss this one. I don't know why. I mean, this still is just a methyl group, right? So we're just looking at methyl magnesium bromide. All the rest of this was the aldehyde. Again, a CH2, the isopropyl thingy, and there it is. And our Grignard is simply the methyl group as methyl magnesium bromide. Other half. We're going to split here. So our aldehyde is a 2-carbon aldehyde. That's acetaldehyde, and that's him right there. And this chunk here, the CH2, the isopropyl, this was our Grignard, looking like that. We've used lots of aldehydes. Let's go ahead and make it just a little bit different. We're going to make a tertiary alcohol here. Tertiary alcohol we can make a couple ways, actually. The simplest is with a ketone. Now, once again, you simply look at what's around your tertiary alcohol. You're going to split something off. You're going to wind up with a ketone half and a Grignard half. We have 3 identical groups here, so it makes it very easy. We'll just split off one of them. Our ketones, so this used to be the carbonyl, simply had ethyl groups on both sides. I think that one works. And our Grignard reagent was simply a 2-carbon chunk, ethyl magnesium bromide. Now there's another way to make this, isn't there? From these starting materials up here. Come on, one more way to make this. We can make tertiary alcohols 2 ways with Grignards, remember. The first way is with a ketone. We just did that. The second way to make tertiary alcohols is with an ester. Okay, I got it. So what you want to do is think what happens to a carboxylate ester. Carboxylate ester adds 2 moles of Grignard, doesn't it? So what we have to do is split off 2 chunks around our tertiary alcohol. Split off 2 chunks, and these were the Grignard reagent that we just added. So, what ester in our selection here do we want? Well, you would be amazed how many people choose this guy. Because it has an ethyl group on one side, right? That's not what you want. Because what is attached here? Oh, yes, that is what you want. I'm sorry. I'm thinking ahead to a different problem. We have the ethyl group coming down this way, the alkoxide left from this position to give us the tertiary alcohol center. So this is the ester we want, and we simply need 2 moles of ethyl magnesium bromide. Now the problem that I just gave away is making this secondary alcohol from somebody up here. Whenever we see a secondary alcohol, we always think aldehyde, right? Unfortunately, if you look at our collection up here, I guess we do have an aldehyde that'll work, you know? Yeah, okay, so I hit that one up there. So this is going to get our secondary alcohol, split on one side, use this aldehyde, and we get our product. Okay? But what I wanted to point out here, and I got ahead of myself on one slide, is that there's one other way to do this. One other way. Now this is the only aldehyde in the bunch, right? So you might sit and say, no, he's wrong again. But remember, an ester, as we just said, can add 2 moles of Grignard. It turns out that we have a couple esters here, don't we? Now, if we took this guy and we added 2 moles of Grignard, we'd have a tertiary alcohol, right? But if we take this guy, a formate ester, remember the hydrogen or the alkyl group survives, doesn't it? What's attached here? A hydrogen. So if we take this formate ester from formic acid, we simply add 2 moles of Grignard to the formate ester. The alkoxide is lost. The hydrogen still lives right here. So we have 2 moles of ethyl magnesium bromide. Any questions? All right, let's just wind it up here with a few very simple carbonyl reactions. Our first one, we have borohydride. We remember the borohydride is a reducing agent. So we're simply going to convert cyclohexanol into cyclohexanol. We just did carboxylate esters and Grignards. We know that they're going to add twice, right? So we have methyl magnesium bromide. We're simply going to add 2 methyl groups to this carbon. We will make a tertiary alcohol. It will have 2 methyls and a phenyl. Lithium aluminum hydride burns in moist air. Nasty to work with, but a great reducing agent. Simply going to convert the carbonyl into an alcohol. And our last set for today . PCC, pyridinium chlorochromate, very mild oxidizing agent, will stop at the aldehyde stage. However, here we have a secondary alcohol, so all we're going to do is make this into the ketone. Cyclopentyl magnesium bromide, and we have an aldehyde. That's going to give us a secondary alcohol. The ring carbon will simply attack the carbonyl, and it will look like that. And finally, we have to remember POCl3. That's different than PBr3, isn't it? PBr3 makes alkyl bromides. POCl3 does eliminations. They're E2, nicely civilized. We will take cyclohexanol and simply make cyclohexene. Now we did this reaction in lab, remember, except we did a very brutal form with simply sulfuric acid, but rearrangements aren't a problem here. E2 is just always nice. Any questions? All right. Look on Blackboard, please. I will put up a sample final exam. Okay? And on Thursday, so try to work through it. On Thursday, come in, and we're going to go through it. Now, make yourself 2 copies of this thing, okay? Because one of them you will take and put your name on, and at the end of the period, hand it in to me. That will earn you 20 points towards your exam food. So that'll help balance out some of the missing points. Okay? Keep one for yourself for practice, and in the other one. Okay? All right. Yeah, question?
So for the final, can we use our own postcards or can we?
Somebody always asks this. Can we use all 3 note cards? Sure. You know, recycle them, I guess. Yeah.
Just to be sure.
Only the last lesson. Yeah, the first one.
That's just a bit.
Or Thursday better, because I don't want to miss the final review. I can take it after.
I teach a lesson to
I have classes all day.
can't do both.
I'll just do it Thursday.
Yeah, okay. Do it Thursday, and you can always move it to